This is a makeup recorded lecture for today class. So up to this point of the lecture, we have been talking a lot of the metering infrastructure for the distribution system, and then we talk about load survey, which is the snapshot of data randomly throughout the entire feeder. So the ideal case for each distribution load is to measure each household one by one to have a smart meter for each of them. And right now, as I mentioned earlier, the average of this IP-based metering infrastructure only have 1 in every 4 families has smart meters. So as you can tell that based on the statistics, what we do is to take a sample of data throughout the year, every season, every part of the system, every kind of load, to do the kind of survey. And load factor and loss factor is something we will go through it today. We will talk about the relationship between the load factor and the loss factor, and how we get the data from, and how we can derive the data from. So as you can tell, that load factor is one way we using instrument can measure the load demand directly, whereas the loss factor is a little bit tricky, so we might have to go through some derivation to come out with a way to quantify load factor or loss factor from load factors. So as I mentioned in the first week of class, measuring total losses is one of the major interests in distribution system. The thing is that since we don't have too many metering data point and the obsolete of the distribution topology, this task can be very challenging. So for the next lecture, I will talk a little about the campus metering load and electrical car consumption for each household, which will conclude this chapter. So for this page, you can see that I have been reminding everyone in the class about the class assignment. Feel free to meet your group member by emailing them as soon as possible, because the earlier the better when you start doing the project. And for those online folks, if you haven't sent me the signed proctor form yet, please do it ASAP. Without having that form received, I don't think you will be able to take the exam at all. So if you get this message, please do make it as a priority soon. And I will be assigning the homework problem set next week. So just watch out on the announcement email that I will be sending out sometime next week. So my plan for this week and next week is that I will be concluding chapter 2. So chapter 2 is a little bit straightforward chapter because there's a whole bunch of metrics that's not so complicated. The ratio with respect to the purpose, how you want to quantify things. And as I said before, this matrix is actually a sample data that has been collected from time to time. So the difference for this basic factor from compared with the one that we have from last lecture, like on Wednesday, is that I'm adding more new information on this plan factors and how we quantify the ratio. And as you can see, that this plan factor is actually the sum of all the energy consumed divided by the maximum plant rating factor. So it's all in megawatt hour instead of the megawatt. And this is a little bit different than the utilization factor. Utilization factor is referred to the load, whereas the plant factor is referred usually to the generating unit. And you also will notice that the diversity factor is actually greater or less than equal to 1, because we have summations of maximum value for each individual customer associated under one root node, which is could be feeder head or could be a distribution transformer. And that's why when you add this up together, it could be a lot of value divided by the DG. So this will result at least equal or greater than 1. And the other factor that I actually add here is the coincident factor, F sub C, which is an inverse relationship from the last one, the diversity factor. So in this case, this will be less or equal to 1 instead of the otherwise. And the tricky part about this is that when we going to introduce contributing factor into this equation, we are going to introduce coefficients for this weighting factor for each demand, because d sub g is actually the sum of all demand individually under the same subsystem. So if there is a need to impose different weight for each demand, then this is the way how we do it: C1, C2, dot 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 Cn. Where you sum out all the C1, C2, and Cn, will be equal to 1.0. And this is how we substitute that as part of the d sub g. And the same thing from this is that this is what affected d sub g, which is the non-coincident factor, or diversify factors. So this will be a lot of factors, as you mentioned. I think the key here is to understand the relationship between those, so that you won't get confused. So I have been talking a lot of location factors, partly because as part of the distribution system, there is a limited number of the metering point across the feeder, as well from the primary side of the network to distribution side of the network. So what we do here is that since we need an initial value for the power flow P and Q, so what we did was we used this to allocate for the child node, which is the load, which doesn't have a metering point, from the root node of the subsystem. And the definition of location factor is the ratio of the meter point of the root node, which could be substation feeder head or any part of the distribution feeder, primary to distribution, as long as it's a meter. As you know, that distribution network is actually a tree structure. So divided by the total summations of the transformer rating. So this refers to the total capacity of the transformer rating. So this is a good example I drew in the class, which is 1K, 2K kVA, 3 kVA, and each of the big dot refer to distribution transformer 1, 2, and 3. So what I did was, if we will have to calculate a location factor, this will be the 1 megawatt. This is again power factor 1.0. So it means purely resistive load. So 1 megawatt, which is the nominal value, divided by 6, because you sum up 1K, 2K, and 3K. So that will be 6 of them. So in this case, you got to watch out the unit here. I don't think I mentioned it during the class today. Is that if you have this in K and this is in mega, you probably have to scale that out to 1,000 times. So that means, if I may correct this a little bit, so I will have this 1,000, and then this will be 1,000. That can change it to kilowatt. So, however, if you want to use it in a megawatt unit, you can actually use the version that I have earlier. So depending on how the preference of your unit, you want to use it. As I said, most of the time after the distribution feeder all the way to the consumer, we usually use kilowatt, the K value, instead of the M value, right? So I just want to point this out so that you are aware of the consistency. So this is another example I show in the class. Unfortunately, that I can't show you the calculator, how I input all this data to the calculator to compute each of those. But this is the same concept as the one that I have explained earlier. So the first question asked is find the S12, which is a complex power consists of if you want to put it in rectangular form, you will have a P plus JQ, or in the magnitude form, which is the apparent power with the angle information. So in this case, we had a power factor of 0.9 and the real power, the active power. Then we will have to use this number divided by 0.9 in order to get the apparent power of S12 with the angle information of 0.9. Since this is a power factor lagging, so there is no negative sign here. So we only have positive sign with the inverse cosine that will result in this result. And the second question asked is what is the calculate allocation factor. Allocation factor is equal to the metering data we just compute from the last question. We include the power factor divided by the total number of distribution transformer rating under that subsystem. So that case we have this distribution transformer, this distribution transformer, and that distribution transformer. That if you have to add it up together, you get this number, and then putting it in the calculator, that will give you this value. The third question will be allocate load to each of the distribution transformer. This is the final part of it, which require us to estimate, sort of allocate the number to each of the distribution transformers. So you have this allocation factor already computed, which is shown here, ST1, ST2, and ST3. So to appropriate this number, you will have to use the distribution transformer rating for each of them. So you see that ST1 will be the AF, the allocation factor, multiplied by 25, give you this number. Likewise for second distribution transformer and third distribution transformer with different rating. This is very useful information that we'll be using for powerful analysis later on when we have this allocation factor figured out, and then have the power transformer rating figured out. Then the computation of the initial PQ value at each load will be straightforward. This is a unique example that I talked about that as well in the class. As you can tell, this part of this is a distribution substation with 4 feeder going out, and our focus here is the 4 feeder. And if you go through this will be a primary distribution network, and the focus here is actually after the distribution transformer DT 427, and under that distribution transformer you have 6 loads. So the question is given is that you have 3 information, then you were asked to find out the diversified demand. So the diversified demand is a D sub G, right, which is the load. You sum out all the load together under this node. So you want to find out what is the D sub G for this transformer. So to do that, you have to understand each of the given the question here. So you have connected load 9 kilowatt per house, and then demand factor recorded, which is 0.65, and diversity factor, which is a F sub D equal to 1.1. So the DG can be defined as a total connected load demand, which is the first one, and then the D sub the demand factors, which is the second one, and then the last one will be the diversity factor, the F sub D. So under this is pretty straightforward. We usually do the load survey conducted in the random fashion, and we selectively pick certain residential consumption and trying to generalize how much the connected load would be. So in this case, it's 9 kilowatt per house. So it's a sum of all of them from 1 to 6, but in this case you're going to substitute 9 kilowatt here multiplied by the demand factor, which gives you 0.65 divided by 1.1 diversity factor. So when you get this nominal value, make sure you do it 6 times, because this is from 1 to 6 with the equal same value, and this is if you calculate it correctly, it should lead to 31.9 kilowatt. So this slide simply show you the breakdown for each of them, the demand factor and the diversity factors, which is the same as what we shown here, the demand factor and diversity factor. And all of this is actually based on the survey of individual data and survey of group data, and then you have to find out the averaging numbers. So it really depends upon how information is given to you before you start working on the problem. And conceptually, if I give you a table of the 6 data from 9 o'clock to 5 o'clock, and you can easily find out the D sub G, which is the in this case it will be the diversified demand by summing out all individual for each time frame. Say if you have 6 of them, you have 6 different types, six of them at a certain time. You just add it out, and then will become 1 point of the D sub G, the diversity demand. So that is really depends on how this information is given to you.